Hey guys, in this video we're going to learn a little bit about Gauss's law. We should already at this point be familiar with the equation from Gauss's law and what each of the things in it refers to, or at least passingly familiar, such as you should know that's the symbol for flux, and that's flux and that's flux, since both sides of the equation represent flux. But in this video we're going to focus more on the question of how do we use Gauss's law, not to calculate flux, but to calculate the electric field? Because after all, that's really the point, is let's use Gauss's law to find the electric field that exists due to some kind of a charged object. Also, please recall the only kinds of objects that we are going to ever analyze with Gauss's law are going to be spheres, cylinders, and planes. All right, other things that we're going to talk about, though, are some of the conventions that I'm going to use throughout this video. Very often, there's going to be a big deal made about the difference between little r and big R. Little r is always going to be the radius of the Gaussian surface, whereas big R is the radius of the object that you're attempting to analyze. Since the Gaussian surface is imaginary, and therefore any size you want, whenever you see little r, that means that it is a variable. Big R, on the other hand, is the radius of the charged object itself. That is a constant, because the object, of course, has a fixed size, whereas the Gaussian surface is limited only by your imagination. Okay, that's a little cheesy, but you get the point, or at least you should get the point. Little r is a variable. It refers to the Gaussian surface. Also, the A in Gauss's law very specifically is the surface area of the Gaussian surface. Also, please note Q enclosed is the charge inside of the Gaussian surface. Throughout the rest of this video, you're going to see me referring to those two terms and specifically using those operational definitions of them. So pay attention during this part, and if you need to remind yourself, go back to it so you make sure you understand what we mean by A and what we mean by Q enclosed. In this particular video, I'm going to address cylinders because we've probably already addressed spheres in class. And so that brings you to example 17 in your notes packet. 17 covers 3 different types of cylinders, because recall we've got 3 different types of charge densities. And so we've got the conducting cylinder, the insulating cylinder, and effectively a wire, which really is a cylinder, just very skinny. The different charge densities, if you recall, are, I'll write them and erase them, I guess. Rho, which is volumetric charge density. Sigma, which is surface charge density, and lambda, which is linear charge density. Remember that rho can only be used on solid insulators. So if it's hollow, don't use rho. If it is a metallic conductor type of a thing, also don't use rho. So rho is what we'll end up using for this middle case when we do the insulator. For the conductor, we'll be using sigma. And when we do the wire, that's going to be lambda. We'll do this in order, starting with the conductor. And first thing I need is a diagram of the object and the Gaussian surface that I am using. Whenever you're trying to analyze a cylinder, you're going to use a cylindrical Gaussian surface, just like how for spheres you use a spherical Gaussian surface. Also, your Gaussian surface is going to generally be concentric. Part A wants to know what the electric field is, and then some kind of a defense of why that is. A fact which you ought to know is inside of conductors, the electric field is always going to be 0. Always. All right, now, why is that? Well, let's write Gauss's law to try to understand why and remember some facts about how conductors operate. So there's Gauss's law, and would probably be tempted to start like plugging in stuff for A and all that kind of a thing, but pause. It's a conductor. Conductors, if you recall, always have their charge located on the outside surface. So all the charge is out here on the surface. Why is that important? Well, in Gauss's law, if Q enclosed is 0, the electric field is also going to be 0. And it is 0 because the amount of charge enclosed within my Gaussian surface is nothing. There is no charge in there because it's all out here on the surface. If it's out there on the surface, then it can't be in the Gaussian surface that I've drawn inside of the object. There is no charge in there. Therefore, the electric field has to be 0. All right, now that is a fact that you ought to just know, and it's also something that you ought to be able to explain. So if I say, what's the electric field inside of this conducting object, you ought to be able to go straight to, it's 0, but also please understand the reason why. You should be able to state that it's because there is no charge in there. B wants us to find the electric field outside of the cylinder. Okay, now in order to do this, we're going to need to actually know some of our geometry formulas about cylinders, such as, especially in this case, the surface area of a cylinder. Most often when we're talking about cylinders, we're only going to be concerned with the what's called lateral surface area. We don't usually care about the ends of the cylinder, and that's because with Gauss's law, we're usually talking about very long cylinders. In fact, technically, for Gauss's law to really apply, it needs to be infinitely long. All right, we can't draw that, so we draw a finite cylinder. But if it's infinitely long, then the end caps don't matter because it's just a tiny little circle, which is negligible compared to the lateral surface area. Okay, now, how do I get the lateral surface area, which would be the curved part? Imagine for a second that this is like a soup can, okay, and it's got a label on it. We slice it down the side, and then we unwrap it. You may be familiar with this derivation from math class, so just bear with me, right? If I take it and I unwrap it, here's what I end up with, is a rectangle. All right, well, the height of the rectangle is, of course, the same as the height of the cylinder. For reasons that will become clear later, we will call that L. So the height of the cylinder is just the L. The other dimension, the width of our rectangle, is, of course, the circumference, which is 2 pi r. So that means that the lateral surface area is 2 pi r L. Mr. Erico, you said just a second ago that the cylinder is infinitely long. Doesn't that mean it has infinite surface area? Okay, yes, but when we do the derivation, you're going to see the L will actually cancel out amazingly. And so the fact that it's technically infinitely long is going to end up not mattering. All right, now, plugging in then, the A in Gauss's law is going to be 2 pi RL. Now, hang on. You may be wondering, is it, like, which R am I supposed to be using? Is it this radius, the radius of, like, the cylinder, or is it little r, the radius of the Gaussian surface? Okay, refer back to what I said in the first part of the video. A is always the surface area of the Gaussian surface. So it's always, therefore, the little r. It's always little r on the left side. Always. Every time. What about this one? No, every time it's a little r on the left side. Don't mix it up. Don't get creative on me, okay? It's always a little r on the left side. All right, for the right side, the Q enclosed. So there were 3 different charge density functions, and if you recall, we said for a conducting cylinder whose charge is distributed along its surface, we use sigma. All right, sigma was Q over A. The charge we are enclosing in this case is the entire charge of the cylinder, because we're outside of the cylinder, and therefore all of the charge of it is what's being enclosed. So Q enclosed is the whole thing. Unlike spheres, though, with cylinders, usually Q itself is not given. Instead, they give you the charge density function. And therefore, we can't leave Q in the answer. We can't just say Q, done. Nope, can't do it. The reason you can't do it is, if you recall moments ago, we said, technically, the cylinder's infinitely long. That means it has infinite charge. Okay, that we absolutely can't work with. So instead, we're going to have to say that the charge is, well, solve this equation for Q, and it is sigma times A. All right, now A, which A? Just a second ago here, A was 2 pi little r L, right? All right, so careful. A doesn't always mean the same surface area. The A on the left side of Gauss's law was the surface area of the Gaussian surface. This A on the right side is the area of charge enclosed. The charge is not on the Gaussian surface, it's on the real object. So therefore, the surface area of charge enclosed, while it uses that same formula 2 pi RL, we're going to use 2 pi big R L, not the little r, because the charge is on the cylinder, not on the Gaussian surface, right? So it's on the real object with the radius of big R, not on the imaginary Gaussian surface that is whatever size I want it to be. Well, a little bit of algebra later, and we have this answer. The insulator is going to be different from the conductor because, automatically, when we're finding the field inside of the insulating cylinder, we can't just assume the answer is 0. In fact, it's not 0 unless it happens to be a completely hollowed out object. If it's not hollow, then there can be charge in here. So this is, charge enclosed by that imaginary red Gaussian surface. Since charge is enclosed, the field is not 0. All right, well, we can make some of the same substitutions we made with the conductor. The surface area of my Gaussian surface through which there is flux is still that same 2 pi little r L. Q enclosed, though, we need a function for that, and for that we are going to use rho. All right, let's see. Rho is Q over V. Therefore, Q is going to be rho times V enclosed. Okay, so we will have rho times V enclosed. All right, the volume of charge enclosed. This should take you way back to one of those basic geometry formulas, which is that volume is the area of the base times the height. The height is L. The area of the base is, it's a circle, so that would be pi r squared L. And notice I'm using the little r because I'm only enclosing some of the charge. I'm only enclosing out to that radius, which is little r, the radius of the Gaussian surface. And if I drew a bigger Gaussian surface out to like here or so, well, then it would enclose more charge. Therefore, the charge enclosed is a variable, and I should be using little r. Okay, do a little bit of algebra. And we have that equation. All right, it's a good enough equation. Notice, unlike spheres, you do not need to replace the rho. The rho can stay, and that's just how cylinders are going to work. For the reason, recall that you can't actually express Q in the answer, because if Q is infinity, because it's an infinitely long cylinder, Q can't be in the answer. Whereas they will, for cylinders, usually tell you the charge density, and therefore charge density may stay in the answer. All right, let's look at outside the cylinder. Now, I'm going to do one of those things where I say, you figure it out, pause the video, and see what you've understood so far. Try it on your own. Seriously do that, right? Pause me. What I will give you for a hint is this. It's basically the same as what you did up above in part C, except for one letter. That's it. There's only one change. So pause me, see if you can figure out what that difference is, and then resume the video. And here it is. All right, I won't make you play spot the difference here. It's there. There it is. It's a big R. Why is it a big R? Well, okay, for Q enclosed, the volume of charge enclosed is not the volume of the Gaussian surface. There's no charge in this area. Nothing there, right? All the charge is on the cylinder itself, and therefore the R that you should use should be related to the radius of the real object, not of the imaginary Gaussian surface. Okay, so we get a different answer from our answer for a conductor, right? There's rho instead of sigma. But notice the answer still depends on 1 over r. So it's the same shape of decay function as you move away from an insulating cylinder. All right, let's take a look at the wire. Part E is not asking for an electric field inside the wire because it says I'll never ask that. Charge density for something like a wire, though, is lambda. It's a linear charge density, right? Charge per length, which makes the radius of the wire completely unimportant. It's not part of the formula, right? Q is just lambda times L. So if it's a linear charge density, you don't care about the radius of the charged object, unless they do something like, say, it's a conductor, and then they're just trying to be sneaky. If it's a conductor, the same rule applies that we talked about in part A. Inside of it, the field is 0. All right, so let's go ahead and answer part F, though. Once again, pause the video, try to figure it out on your own, and then resume me. Do that. All right, here's the answer. All right, looks good to me. All right, now one overarching point. Please notice that that part didn't change through the entire question. Inside, outside, insulator, conductor, wire, whatever, the surface area of a cylinder formula that you're going to use is always that 2 pi little r L. Never a big R, never a different formula, never the volume formula, 2 pi little r L. Always the same thing. All right, last thing I want to point out before we go. Sometimes the book will do this awful thing to you where they express this electric field as follows. I don't know why the book decides sometimes to put it like the one on the left and sometimes the one on the right, but they do. And here's the deal. Since Coulomb's constant has this value, meaning it's related to the constant epsilon naught, sometimes they will make substitutions and replace things related to 2 and pi and epsilon naught with k. So if you take a moment and think about it, you can see how you could go back and forth between those two ways of expressing the electric field. I don't care which one you use. I'm only mentioning this because I don't want you to get the answer and have it right and then look at what the book has given and then you're like, dude, what? And spend 15 minutes redoing the problem just to realize that this is all that's happening. Okay, that's it. Thanks for watching, guys, and I hope this helps.